Okay, so should we do our PowerPoint now?
Yes.
How do I get out of this?
I don't have anything.
You just want to like go off on the slides.
Yeah.
I'll start. So we did experiments with a Tesla coil, which is that right there.
This is Nikola Tesla, the creator of the Tesla coil.
Yeah. Apparently not very well known physicist, but he's important for a lot of light right now, like balls like that. So okay. So a Tesla coil, what it does is it takes voltage from something like this wall, and it makes the voltage super, super high, like this one we found was 100,000 volts. But it also increases the frequency a lot, so it's not as dangerous. Like I got shocked by that a couple times. It didn't hurt very bad because the frequency was so high.
It's very low current.
Yeah, and so that's kind of what it looks like. It acts like a transformer, but it also increases the frequency, which they explained, but it was kind of confusing. So as you can see, there's just not very many coils on there, and then attached to the actual ball thing, there's a lot of coils, so it has a very high voltage.
This is our experiment. We tested the dielectric breakdown of 6 different materials. We have marble, glass, rubber, wood, mica, and paper.
Okay, so we have processed in order of increased dielectric strength, which means the top one would be the one that the current can get to the easiest. We thought it'd be glass, then marble, then wood, paper, rubber, and mica. And mica, it's this little like weird kind of like a foam rock thing, but we read in our book it has a really high dielectric strength. They used to use it in old capacitors, so it's kind of cool. That's just a huge bucket of it.
So our first procedure didn't work very well. I will demonstrate this and then explain it.
Here, if you want to
Yeah. So we had the. Can you turn on this thing again?
Yeah, I don't know how. I guess I can't.
Ooh, I got that.
No, press escape. It's no problem. And you just minimize the window. It's down. Down, 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 down. Down, it's on the bottom. You minimized it. There you go.
Oh.
So we would measure how far between the ball and this rod that the electricity would go through the glass.
Yeah. We try to find sort of the maximum distance there we
But
go.
we found out. Oh, you have that thing.
What?
Like, this is what we're doing.
Yeah.
We found out that it was actually going through air most of the time and then through glass as little as possible. As with in a similar way with
The light thing.
what was it called?
When like
The
when like the
diffraction
lifeguard's
thing.
swimming. So it would find the fastest path through the material and through the air, which was pretty hard to measure because we didn't exactly know the path. So we thought of a
It
different
was like index of refraction.
Yeah, different something like that. So we thought of a different one. We wanted to make the distance, the only way it could go would be straight through the material so that it wouldn't go through the air at all. So like we had this, we just had it straight above. We luckily found this little knob right here. It could change the voltage. So we just had it like that directly above, and then we decreased the voltage until it would just barely happen, and right like at the point when it would have a current, then we would take that thing off and find the maximum distance that it would go across air, since we knew the value of air. And sometimes did this, it didn't work well, but
It's not working right now.
yeah. Just keep it like this. So, and then like that, we would find out the maximum distance, and we would use that to find the voltage, and we'd measure the thickness of this, so we know the distance to travel, we know the voltage, and from that it's pretty easy to find dielectric strength. So here's some of the results we got. This is the
Mica
thickness.
had the highest dielectric strength.
Yeah, we'll show you. We actually found the dielectric strength in each of these, and this is in volts per meter. So it's glass and wood, marble, rubber, paper, then mica. Mica was pretty big. So
It was like an extremely thin piece of mica that we had to use to get it to.
Also, if you guys want to bring up anything, we can find the dielectric strength of something. If you guys want us to do that.
There we go.
What?
Cell phone?
I don't think it would be great with a cell phone. I'm not sure
Gum?
if it would still work. Gum?
Yeah,
Yeah.
try
let's do it.
gum.
Would it burn?
About water.
Do you have a caliper?
Is it
Water-
pre-chewed or not?
water's not a-
Fresh
the
piece.
only thing fresh piece.
Yeah, water's a conductor, so. Are you still filming this?
I am still filming this. This is real.
I don't even know what a caliper is.
Minimize, minimize.
You stuck it in something.
Yeah.
Maybe you can edit out this part.
Right, maybe. I'll get a caliper.
Oh, I found one.
So this is real live physics here, huh?
Yes.
Yep, we're doing this live.
Alright, so do you want to plug it in? Oh, it's going like this. Okay,
So
so
you might want to rotate the camera. It's upside down.
is it?
This is your hand. Yay.
Here's where we're going right there. So, the hard part of making sure it's directly on, yeah.
That's dumb.
Okay, so you're going to be adjusting. Ah, it's like going.
Can you rotate your hand so that we can see when the spark goes?
Well, it's going now. We just need to. It's like melting the gum.
Aww.
Ah.
This.
Was that it?
Yep. Now I gotta get it to work with this. Yeah, the caliper.
Like that. Sometimes the Tesla coil would stop working, but.
There.
Ah. Okay, so 1.4, the thickness of the gum was.
So they're just taking a ratio of distances and multiplying that by the dielectric breakdown of air?
0.4.
Does that make sense?
Yeah.
You want a calculator?
I don't use mine.
They're measuring the dielectric breakdown of gum. That's sick. It is sick. It melted the gum. Thank you.
So about 10 to the 6, 10.5 to the 6 volts per meter. So.
Yeah! That's like science!
Yeah, if you had a meter of gum, you need a pretty high voltage.
10 million
10
volts
million
would go
volts.
through a meter of gum.
I have a meter of gum.
No, but I wish you did.
Should I bring in a meter of gum someday?
We don't have 10 million volts either.
Wait,
Yeah.
hold on. Do you think those rolls are a meter? The
You
hubble
need to
bubble
have a
rolls?
thickness, and
Yeah.
it need to be really wide, because electricity prefers to go through air rather than
Air
go
is
through.
about a third of gum, so Mitch, I'm just gonna throw this away because it's kind of melted in weird places.
That is fine.
He wanted to eat it.
Yeah.
All right, thank you guys. Very good.